Many equations and graphs we use are shadows of a more elegant, higher-dimensional mathematics. To understand the true shape of these concepts, we must step out of the real number line and into the dimension of the imaginary number y. The core of this journey starts with the intuition gap in the early 1700s. We know 2 cubed means multiplying 2 by itself 3 times. But what does raising a number to an imaginary power, like 2 to the power of the square root of -1, truly mean? In 1712, a clash erupted between the co-founders of calculus, Leibniz and Bernoulli, over the logarithm of a negative number. Leibniz argued it was impossible, while Bernoulli claimed it was 0. This stalemate lasted over a year, but ultimately, both masters were wrong. In 1747, Leonhard Euler intervened. He proved the masters wrong by showing log -1 is imaginary. Yet, this led to a new crisis, Euler's paradox, where the rules of logarithms suggested 2 by equals 0, a clear contradiction. Euler was tormented by these difficulties. To solve Euler's paradox, we stop thinking algebraically and start thinking geometrically. Henry Briggs, the inventor of common logarithms, had a key insight. If you zoom in far enough on any exponential curve, it eventually looks like a straight line. This insight allows us to turn curves into lines through linearization. Briggs used 54 successive square roots to zoom in. In this tiny neighborhood around the y-intercept, the complex curve of y equals 2 to the power of x behaves like a simple line. Briggs found the slope for base 2 was an awkward 0.693. By changing the base to force the slope to be exactly 1, we discover the mathematical constant e. The number e is the unique base, where the function's slope at 0 is exactly 1. This leads to an algorithm for exponents, often called the compound interest formula. We divide by n to zoom in, calculate the value using the straight line approximation, and then raise it to the power of n to zoom back out. This machine can now handle any input z. What happens if we inject an imaginary number, like I, into Briggs's linear machine? Let's use a small zoom factor, n equals 6, for an experiment. Geometrically, the term 1 plus I over 6 is a complex number with a real part of 1 and an imaginary part of 1/6. When visualizing the input on the complex plane, our linearized term forms a thin triangle. For very large n, the magnitude is approximately 1. The angle, delta, is approximately 1 over n radians. This shows the difference between growth and rotation. Real exponents cause growth, as magnitudes multiply. Imaginary exponents cause rotation, because angles add. We don't grow outward, we rotate. The pivotal insight leads directly to Euler's formula. Since the base of our triangles was 1, the final distance from the center stays 1. Exponential growth, when rotated 90 degrees by I, becomes circular motion. Euler realized that logarithms have infinite answers, not a single one. Because it's a circle, log -1 hits every rotation. Leibniz and Bernoulli were fighting over a single point, missing the infinite periodic nature of the complex exponential. The true shape of this function is the analytic landscape. Projected one way, we see exponential growth. Projected the other, we see sine waves. Euler's formula proves these two distinct concepts are actually the same structure viewed from different angles. Applying a rotation of pi to Euler's formula yields what many call the most beautiful equation. This structure unites algebra, geometry, logic, and imaginary numbers into a single, unified truth, revealing the hidden geometry of the universe.